in this region, we have normally reduction of amplitude. In this region, the amplification. Okay. For this system, what we have is the curve is like this. The response X compared with F0, because I divide K, meaning that I am comparing the excitation force with the force acting on spring. Okay? The curve looks like this. This is 1. And this is 1. R. I have curve. This. Okay? Remember? Meaning that at low frequency, the behavior is similar, at high frequency, behavior is different. Yes, sir?
A peak, I think, yeah. That's right.
You got knowledge. Because that is square root of 1 minus zeta square. Zeta is smaller than 1. Therefore, square root of 1 minus zeta square is smaller than 1. Therefore, the peak has to be on the left-hand side of I. That's right. Now, recognize that there's nobody before I made a mistake. So, I know that I reserved one or several oranges. So, you finally got one orange this one. All you guys buy all of this. Okay, now it's clear, right? Because I made a mistake, everything is clear. Okay, another interesting point. This analysis is valid or is good to design the seat, right? I want to design the seat so that I can feel minimum X. How to make a K, how to make a C. Okay? So seat design is very attractive. Not only deciding the color or the shape, determining C and K is very important in this regard. However, due to the vibration of base, there will be the force transmitted to the base. Okay? How much force is transmitted to the base? Due to the base excitation. And that is also very interesting. So let's consider the force transmitted to the mass. To the mass or to the base. Okay. Let's consider to the mass force. Then using free body diagram, we can because F equals ma. The force transmitted would be equal to K x minus y plus C. Or and we do know the solution, therefore we can calculate the magnitude of force transmitted compare with the force transmitted, a force exerted to the spring, that is Ky, can be written as like this, R squared the difference is what? Comparing this, the difference is there is a factor of R squared. Okay? And if I draw this, this is R, and I want to see force transmitted normalized by and this is Y. Okay, what if when R goes to 0? When R goes to 0, the whole term rapidly decays as R goes to 0. So rate of decreasing in amplitude is very rapid compared with this. This slowly decays as R goes to 0. But this rapidly decays as R goes to 0. Meaning that the force transmitted to the mass or base will be rapidly decreasing as I change my excitation frequency to 0. Because as I demonstrate, when I move up and down, there's no force is transmitted to the mass, because, right? Right? Just the static. There's no dynamic force. And this will look like this. And also we found that at square root 2, we have 1.4 instead of 1.0. And then interestingly, when I have big damping, even we have amplitude in high frequency is bigger than 1.4. And another damping. The same behavior. I would highlight over here, more rapidly decaying. Amplitude goes up as zeta goes up. Not amplitude is not decaying. So I ask you to draw these 3 graphs at the same time on your note. Write down the governing equation and the solution, and draw this picture on your note, and examine what you learned from those graphs in comparison. And the text has a good graph but in separate page, so maybe good idea you draw the graph at the same